this topic, we'll be looking at exponentials and logs, but this particular exercise focuses on just the exponential function. Let's begin by taking a look at the relationship between exponentials and logs. If I start with the number 8, I can rewrite that as being 2 times 2 times 2, which of course is 2 to the power of 3. This is just the standard form, and this here is the index form. So I've got base 2 raised to the power of 3 equaling 8. Usually this 3 we consider as being the index or the power, but we can also refer to that as being the logarithm. Another way of writing this relationship between 2 and 8 is to write it in a logarithmic form. So here you can see I've got log base 2 of the number 8 is equivalent to 3. So really what we're asking here is, say, if we begin with number 2, what do I need to raise it to the power of to get an 8? And the answer for that is a 3. The statement on the left and the statement on the right are equivalent to each other. So 2 to the power of 3 equaling 8 is the same thing as saying log base 2 of number 8 is equivalent to 3. Let's look at it. Here on the left hand side, I've got base 2 raised to the power of 3, the result's 8. And on the right hand side, I start at 8, I'm taking log base 2 of number 8 and I get a 3. So on the left hand side, in this statement, the input is 3, the output is 8. And then on the right hand statement, the input is 8 and the output is 3. You can see that these two statements or functions undo each other. That is, that they're inverses. Now, I like to show that connection between indices and logs using that example there with 2 to the 3 equaling 8, log base 2 of 8 equaling 3, actual numbers, but you can use, and you could show that also with just these letters here. I find this version much easier to remember. As I've said before, they undo each other, the exponential and the logs. And they're very similar to multiplication and division. So if I start at 2 times by 3, I get a 6. And then if I have a 6 divided by 3, do the exact opposite of multiplying by 3, then I get back to the 2. Same thing with the sine function. So if I have sine 30 degrees, if I take sine of 30 degrees, the result will be 0.5. And if I take inverse sine of 0.5, I'll get to 30 degrees. And here you can see the same thing applies with addition and subtraction. So now let's just focus on the exponential function. Let's consider this situation. We have a flu virus that initially has a mass of 20 milligrams, and it increases exponentially at a rate of 30% every 10 minutes. So that's an increase of 30%. So in other words, it's a multiplying factor of 1.3. At the very beginning, I have 0 lots of 10 minutes that have gone by, and the mass is 20 grams, or 20 milligrams. After 10 minutes, 1 lot of 10 minutes, then I have my initial amount multiplied by 1.3. After 20 minutes, then I have what I had previously, which is 20 times 1.3, and then I take that, I multiply that by another 1.3. And if you like, I can write that as being 20 times 1.3 squared. After 30 minutes have gone by, then I have what I had previously, so that's 20 times 1.3 squared, and I multiply that by 1.3. So in other words, it's 20 multiplied by 1.3 to the power of 3, and that continues on. So after 60 minutes, then I end up with 20 times 1.3 to the power of 6. So after 1 hour, the virus has grown from 20 milligrams to approximately 97 milligrams. And that can be just found using this. The model that we could use is the mass is equal to 20 multiplied by 1.3 to the power of t. We think of the 20 as being the initial mass. We think of 1.3 as being the multiplying factor, and then t is the amount of time that's gone by in 10-minute increments. The general rule for any exponential is this. And you would have seen this from Unit 1. But we've got the base A, and in our case that's the 1.3. We've got a dilation factor of A here, capital A. We've got a dilation factor here, or a multiplying factor as far as x is concerned, of k. And in this case, I've got the x plus b here and the plus c. So remember, the capital A represents dilation factor running parallel with the y-axis. The lowercase k would represent a dilation factor of 1 over the magnitude of k parallel with the x-axis. The b takes into effect the horizontal translation, so shifting it left and right, and c takes into effect the vertical translation, shifting it up and down. And we'll go into specifics of that a little bit later on. Please note for this example here in the notes, I've made a mistake. A, the dilation factor at the very beginning, wouldn't be 1 in this case. It would in fact be 20. So if you just amend your notes, please, and make that a 20. The multiplying factor, or the base, is 1.3 still. And k is 1, and that wouldn't even be shown. B would be 0, there's no horizontal translation. And c is 0, there's no vertical translation with it. So if we throw those in, of course a being 20, we'd come up with this rule here. And that would be a model that works for that table of values. Okay, so here we have a function f of x defined. It's 12 multiplied by 3 to the power of x. Calculate the following: f0, f2, f of negative 2. Now the key to this here is that we've got a base of 3. 3 is greater than 1, so therefore this is an increasing exponential. If the base is a fraction or a decimal, it's a value between 0 and less than 1, then what you'll see is a decreasing exponential, but this is an increasing exponential. So I state the rule with the substitution of x equaling 0, I get 12, x equaling 2, I get 108, and where f is equal to negative 2, then it's going to become 12 times 3 to the power of negative 2, and I can rewrite 3 to the power of negative 2 as being 1 over 3 squared, so it becomes 12 times 1 over 3 squared, which ends up being 12 on 9, which simplifies to being 4/3. Here are our index laws. So if you've got a certain base a to the power of whatever multiplied by that same base a to a different power, simply add the powers together. If it's in brackets, we multiply the powers together. If we have a negative power, then we can rearrange it so that it's 1 over that base to a positive power. Here we've got the nth root of a, and that's simply equal to a to the power of 1 on n. And the most common occurrence of this type of rule is when we have a squared. So if I had the square root of 36, then for mathematical convention, I wouldn't even worry about putting the 2 in there. I wouldn't write that in. I would just assume it's a 2. And so I'd have the square root of 36 would equal 36 to the power of 1 on 2. And that's how we get to that power of a half. Over here on the right-hand side, we've got base a to the power of m over base a to the power of n. We just subtract. This rule here is quite interesting, and it occurs all the time, but here we've got a to the power of m divided by a to the power of m, so it's the same powers. So think of it, we've got some junk here divided by exactly the same amount of junk. Of course, the result is going to be 1. Take anything and divide by itself, the result will be 1. If we follow the index law above, then we're going to have a to the power of m take m, which is, of course, a to the power of 0. So we end up with this important part, which is a to the power of 0 equaling 1. Just remember that you can treat your brackets like so you can have that power and then say, okay, what's the same thing as a to the power of n being multiplied by b to the power of n? And here, a to the power of a fraction, we can write that as being a to the power of m and then take the nth root of it. Or we can treat this as being the nth root of a, get that result, and then raise that to the power of m. And you'll end up using 2 different ways depending on the situation, depending on the numbers that you've been dealing with. One will be quicker than the other if you're trying to simplify. Let's look at some examples here now. So for a, we've got 36 to the power of 0. Anything raised to the power of 0 is 1. For b, we've got 36 to the power of a half, so we know that that's the same thing as the square root of 36. And don't forget, you're going to have both a positive and a negative version for this, so we get plus and minus 6. For c, we've got 36 to the power of 6 on 4. That simplifies to being 36 to the power of 3 on 2. And using that last index law, I can write that as being 36 to the power of a half, get that result, and then raise that to the power of 3. And alternately, I could have written that, okay, that's 36 to the power of 3, and then take the square root of that. But obviously, this version here is easier for me to work with rather than trying to work out what 36 cubed is. So follow my logic along here. So I've got 36 to the power of a half. That's the same thing as the square root of 36. And all that's raised to the power of 3. Of course, the square root of 36 is plus or minus 6. And all of that then is cubed. So I end up with positive 6 cubed or negative 6 cubed. And 6 cubed ends up being 216. And negative 6 cubed, so negative 6 times negative 6 times negative 6 is negative 216. For D, I've got 1 on 16 to the power of negative 4. So I can bring the bottom part of the fraction up and rewrite that power as being positive 4. Of course, this is just 1 to the power of negative 4, so 1 to the power of anything is still going to be 1. And 16 to the power of negative 4. So this could be a step in here, which has 1 over 16 to the power of negative 4. Then my next move is to write that as taking the 16 up, so 16 to the power of 4. And then 16, I realise, can be rewritten as being 2 to the power of 4. And all of that then is to the power of 4. And I multiply through, so it's 2 to the power of 16, and ends up being 65,536, which is a large number. You know, very unlikely that you're going to have to evaluate that in an exam 1 kind of situation. But there's the workings there. You can do it. All right, let's take a look at some simplifications now using index laws. So for A, we've got base 3 to the power of 2x take 5 being multiplied by base 3 to the power of 6 minus 3x. So the trick for this, because we've got multiplication, same base, then just add the powers. End up with 3 to the power of negative x plus 1, which we can rewrite as being 3 to the power of 1 minus x. For B, we've got the same base, 13, but we've got a division going on. So we can rewrite that as being 13 to the power of 6q take 3 over 13 to the power of 4q take 7. We've got a division, so the idea here is that we subtract the powers. So it's 6q take 3 minus 4q take 7. So the mistake here that students mostly make is not to put this in brackets and therefore mess up this second term. So 6q take away 4q will give me 2q. Negative 3 take away negative 7 will become negative 3 plus 7. And of course that there is positive 4. Okay, for C, I've got 8 lots of 2f minus 3 multiplied by 16 lots of 4 minus f all over 4 to the f plus 2. So straight away you should realise that the 8, 4 and 16 can be rewritten as 2 to the power of something. So 2 to the 3, 2 to the 4, 2 squared. In that format we can just multiply the powers. And so you can see what we've got here. The top line, we've got multiplication, so now we can add the powers. So 6f plus negative 4f and negative 9 plus 16. And that's all over here, so you can see I've done that with workings. And the continuation of it, I have 2 to the power of 2f plus 7 over 2 to the power of 2f plus 4. We've got a division taking place. Same base, so now we can do a subtraction, so it's the top power minus the bottom power, and I put that in brackets. So 2f take away 2f is 0f, and then 7 take away 4 is 3, and of course 2 to the power of 3 is 8. So we go from this complicated expression for C to just 8.